All right, time for the hard part. What happens if direct substitution is not possible? You'll know that it's not possible if you have something like this guy right here. Limit as x approaches 3. Well, okay, let's see if we can substitute that 3 in. Oh, look, conveniently it's right there. It's even starting to simplify itself. What? 0 over 0? What the heck is that? Ah! So direct substitution did not work for this problem. And the reason for that, again, it wasn't possible here because it results in a 0 in the denominator, which made this whole sucker undefined. 0 over 0 is actually a really common thing to happen with direct substitution. It gives you what's called indeterminate form, because 0 over 0 is undefined. However, it's tempting to say, nah, the limit doesn't exist, we're done. But that's not true. If we look at this function, I have it graphed here in Desmos in blue, there is a limit when x is negative 3. The function isn't defined there. I'll turn off that highlighter. Here we go. The function is not defined at that value. Duh, I wanted positive 3. The function is not defined at this value. Note that if I scroll over there, we see 3 comma undefined. So there's no function value there, but the limit clearly exists as we approach from the left and as we approach from the right. We definitely approach a value. Looks like about 0.125. Looks to be about where we're getting both on the left and the right. So there is a limit there. We need another tool. Direct substitution just didn't work here. So one way we can evaluate limits when we're talking about polynomials in the numerator and denominator is to bring back our favorite F word, factoring. So if we actually look at that exact same problem, x minus 3 over x squared plus 2x minus 15, we can rewrite that as x minus 3 over x plus 5, x minus 3. Because again, 5 and negative 3, those multiply to negative 15, and they add to 2. So this method is sometimes called a dividing out method, because note, you have an x minus 3 on top, an x minus 3 on the bottom. Those cancel. They actually create a hole. When you have factors that cancel, there's now a hole in the graph, which is the reason for our indeterminate form. We don't care about that so much as, now I have a much simpler function to work with. Well, the limit of the original is going to equal the limit of this one right here. And conveniently, this is a function where direct substitution works. That'll be a 1 over 3 plus 5, which is just 8. 1/8, sorry. Again, that does match up with what we saw on the graph. 1/8 is 0.125. So this function does approach that value. So the goal is to use factoring to turn our functions into things that we can just use direct substitution. All right, let's look at another example. Note that direct substitution wouldn't work here. -1, if I tried to substitute that into x, would give me a 0 in the denominator. So we don't want to do that. Factoring that numerator, two numbers that multiply to -8 and add to -7, that's just going to be -8 and -1. +1, sorry. We also have that +1 in the denominator, so once again, these divide out, giving us an equivalent function. It would just have a hole in the graph. No big deal, though, because we can substitute that -1 into this function. That would just be -1, take away 8. So this limit is going to be -9. If you would like to go ahead and make a graph to confirm, I promise it does work. Factoring strikes again. One more quick quadratic one. Now 2, we couldn't just do a direct substitution. 2 squared is 4. 4 minus 4 is 0. Not going to work. But once again, a bit of factoring can save the day for us here. Two numbers that multiply to 6 and add to negative 5, well, that's just negative 2 and negative 3. In the denominator, x squared minus 4 is a difference of squares. So that's an x minus 2, x plus 2. Once again, get some factors that cancel. They would cause a hole in our original graph. And now we have something that we can just do a substitution on. We wind up with a 2 minus 3 in the numerator and a 2 plus 2 in the denominator. So 2 minus 3 gives us a negative 1, 2 plus 2 gives us a 4, and that will be our limit as x approaches 2 of the original function. So here we can see factoring pretty quick, especially if you remember your math facts there. Hey, multiply to 6, add to negative 5. Much quicker than putting this whole function into your graphing calculator. Definitely quicker than putting it into Desmos with all the weird sliders and everything there. Once we jump over to number 4, remember, not all of our factoring patterns are as easy as what two numbers multiply to 6 and add to negative 5. In number 4, that's a grouping problem. So taking a look at the top there, taking a look at our numerator, x cubed plus 4x squared minus x minus 4. That's a grouping problem. Out of those first two terms, I could pull out an x squared, and I'd be left behind with an x plus 4. And then out of the second two terms, I could pull out a negative 1, and I'm left behind with an x plus 4. That should have been red. With a grouping pattern, the goal is to look for those matching left behinds, and those become one of your factors. And then the other factor is the GCFs, the terms you pulled out, the x squared minus 1. So that's a factoring pattern that is admittedly a bit more intense than the previous couple examples. Note x squared minus 1 can actually be factored further, because that's a difference of squares. So that can be factored to x plus 1, x minus 1. In number 4, yeah, whether factoring is quicker than graphing really depends on how quickly you recognize those factoring patterns. As far as the bottom, I don't know why that's coming up. As far as the bottom is concerned, that's just a GCF pattern. So you could factor a 2x out of both of those terms. You're left behind with an x plus 4. So on the top, we have this blue, this black and red mess. On the bottom, we would have a 2x and an x plus 4. So we do have some stuff that cancels. X plus 4 cancels off with x plus 4. That would create the hole in our original graph. Nothing else cancels, but it's okay because now I could substitute that negative 4 in for all of these x's. So let's go ahead and do that, finish this problem out. So we would have a negative 4 plus 1, a negative 4 minus 1, and then in the denominator, 2 times negative 4. So this isn't too bad. Negative 4 plus 1 is negative 3. Negative 4 minus 1 is a negative 5. Multiplying those together gives us a 15. In the denominator, 2 times 4 is 8. Positive times a negative makes that whole fraction negative. And that is our limit. So certainly some of these factoring problems are more intense than others. Let's go ahead and do one that's a full-on split in the middle. Taking a look at number 5 here. Our top is just a plain old regular what two numbers multiply to negative 24, add to negative 2. So it isn't the top that I'm concerned about. Negative 6 and positive 4 are two numbers. The bottom, however, is a full-on split the middle. We would need two numbers that multiply not just to 12, but to 12 times 3. So two numbers that multiply to 36 and add to negative 20. So it's been a while since we've had to do that. Two numbers that multiply to 36 and add to negative 20. So your two numbers are are negative 18 and negative 2. Those become the numbers that we split the middle with. We get a 3x squared minus 18x minus 2x plus 12. Again, when you're doing a split the middle problem, finding those two numbers, those aren't your factors, they're just there to help you find your factors. After splitting the middle, it becomes that grouping problem where we're looking for GCFs. What can I pull out of both? A 3x squared and a negative 18x? Oh, well, 3x. Got it. I'm left behind with an x minus 6. On the right-hand side, I can factor out a negative 2. And I'm also left behind with an x minus 6. Note that my left behinds match. That's what I want. That's how I know that I split the middle correctly. So our two factors wind up being 3x minus 2 and x minus 6. So note that that's my bottom. My top had an x minus 6. My bottom had an x minus 6. So when I go to create my fraction with both the numerator and denominator factored out, those are going to cancel. That's going to give me the hole in my graph. So I still have an x plus 4 in my numerator, and I still have a 3x minus 2 in my denominator. So quite a bit going on in this particular problem. The goal was to find the limit as x approached 6. So now that I have removed that x minus 6 from both the top and the bottom, I no longer have the indeterminate form. So I can substitute that 6 back in. So we have a 6 plus 4 on top, and a 3 times 6 minus 2 on the bottom. 6 plus 4 is 10. 3 times 6 is 18. Take away 2 gives me 16. And we can reduce that sucker by 2. Yikes. So a grouping problem can definitely show up in one of these factoring in order to use direct substitution. The other thing that can show up are some of those Algebra 2 factoring patterns that we really haven't played with a ton in pre-calc. Taking a look at number 6 here, in the numerator, that's a sum of cubes. So it's likely you haven't messed around with a sum of cubes in a while. If you don't quite remember that one, if you just Google sum of cubes, it will pull up the formula for you. The way we remember this one is SOAP. Same, opposite, always positive. In other words, my signs are going to match and then change, and the last one is going to be positive. The cube root of x cubed is just x. The cube root of 8 is 2. So my first binomial is going to be an x plus 2. And then when I go to build the trinomial, I'm going to have an x squared, pardon. My last one will be a 2 squared, which is 4. And my middle term will be a 2 times x, those two cubes put together. Again, if you don't remember your sum of cubes pattern, a quick Google search will give you the full rundown there with A's and B's, the way you probably would have learned it in Algebra 2. I usually remember them as just SOAP problems to get comfortable with the different signs there. So it's been a while since we've had to play around with one of those. In the denominator, two numbers that multiply to 20 and add to 2. Add to 12. Add to 2, but not a word for us. Add to 12 are going to be x plus 2 and x plus 10. Note that once again, hey, stuff cancels. That's going to create our hole. So now we are good to do our direct substitution. Now that we've gotten rid of the problem, there's no more x plus 2 in the denominator, we can substitute that negative 2 in. So not all of our factoring problems are the light and breezy guess and check kind. Alright, so we have our substitution taken care of there. This is probably one where I'm going to go ahead and let robots do the robot work. So let's pull out that calculator and let it rip. So we had a negative 2 squared in the numerator, along with a 2, another negative 2. 2's everywhere, plus 4. And then in the denominator, negative 2 plus 10. And go. Wind up with a 1.5. If you wanted that as a fraction, there we go. Scrolling up without these squiggle equals will give me the fraction there, 3/2. So it is definitely worth noting here that, that was a tough problem. The one before it, just as tough. If you're looking at these factoring problems and you're thinking, man, it would be quicker to just graph or use a table, I think on 5 and 6 I would agree with you. Looking at a graph, looking at a table probably would be quicker. However, problems like the first couple, or even number 3 with a difference of squares there, it is quicker to do a guess and check factor and a quick cross off than to actually program your calculator to have the function in there and open up a table and look at, in the example of 3, we'd look at 1.997, 1.998, 1.999. It is more time consuming to use a table than to quickly factor. So if your factoring's a bit rusty, you probably want to brush it off for this section and, also because there's a final coming up. Additionally, if you are still watching at this point, congratulations. Earn a hidden bonus point by sending me an email. Tell me how the sub's doing. See you soon.